Hello, everyone. I hope you are all doing great. Today, I will start our lecture by going through the lectures 7 and 8. Those are really main important two topics. In chapter 7, we will talk about some topological notations, the notations of a function, and the introduction into the limits of a function from the theoretical point of view. Then chapter 8 will be dedicated to how to analyze limits in multi-variable functions. This is really a very important topic, and it needs your focus, and it will need you to memorize all the definitions that we will try to go through. The first part of our lecture will be dedicated completely for the most of the topological definitions, starting from an open ball, the interior of a set, the exterior of a set, the boundary, the closure, and stuff like that. Then we will go through the definition of the limit and how to evaluate the difference between the limits in one dimension and the limits in two dimensions. Ciao. Okay, let's start with this definition of the open ball, and it's one of the fundamental concepts in topology and analysis in general. The definition of an open ball, it can be defined as this. I will read it and then I will make a simplification for the idea. An open ball centered at a point x node belongs to Rn with radius r greater than 0 in the set of all points in Rn where there is an r greater than 0, okay, where all the set of these points distance from x node is less than r. So if you need to read the notation or how it's written, it's really very simple. All you have to do is to take this writing like that. This is B of x node and r, and it is the set of x which belongs to Rn such that the condition is the magnitude of x minus r, or x minus x node, x minus x node must be less than r, as you can see, and this is the set of the points of an open ball. Also, we can write it or symbolize it by this symbol beta or b of r, that's x node, which means the open ball of around x node. So x minus x node is the Euclidean norm or the Euclidean distance, which is simply the difference between the components between x node and between x1 and x node, where this is the norm, and it can be represented like this. That's an open ball, so it is the set of the points where r is greater than 0 but less than the distance connecting x minus x node, and these are all the points, of course, without the boundaries. Remark in geometric intuition, for a real number or for R1, if we are talking about R1, here is the x-axis, negative infinity, and that's positive infinity. So for value like x node, the open ball, by the open ball, we mean the open interval, which is centered at x node, and it has an r to the right and r to the left, so it's becoming the boundaries. The upper bound, it's going to be x node plus r, and the lower bound, x node minus r. Also, one of the famous notations that's used with open balls is to consider, instead of r, just epsilon. So we can say exactly the same definition as you will see on the slides shortly. It's the norm of x minus x node, and it is then less than epsilon. And here also we can write it as I told you, it is the open interval x node plus r, and this is x node minus r, or writing it as x node plus epsilon, x node minus epsilon. It is exactly the same as I told you. Okay, This is the definition in R1. If we are talking about R2, so we are talking about a unit circle like this, which is gonna be the interior of a circle excluding the boundary. As we saw here in the 2 dimension, it is a circle without the boundaries. That's what's called an open ball. If we are talking in R3, if we go to R3, then we are dealing with a sphere. Okay, so we are dealing with a sphere, and where x naught is really in the center, and this is R, which is defined by the Euclidean law or the Euclidean distance. If we are generally in Rn, it's going to be the set of points strictly inside an n-dimensional hypersphere. So mainly you can think of an open ball around x node as the circle entiring or around x node, but without these boundaries. This definition is really very important. Once more, this is the definition using epsilon. So that's an open ball around A with epsilon, where epsilon is greater than the distance separating x than A, which is the magnitude of the node. If we are talking in R, so in particular, it's going to be the open interval, as I told you, which is x node plus epsilon, x node minus epsilon, as you can see. In R2, it's going to be the magnitude of xy minus a and b. So this is an interpretation of the symbolizing in case of R2. R3, it will be the same, but you will have the z component appearing here, because we, instead of dealing with a circle, we will be dealing with a sphere. And this will drive us to the second definition, which is an interior of a set. What we mean by an interior of a set? An interior of a set, it means all the points, okay, with open balls that already fit inside and this set. So it's written that A belongs to Rn. The interior of A denoted by int A, or sometimes A node, is the set of all interior points of A. In interior points, a point x is called the interior point of A if there is just an open ball, okay, a subset of A for some r greater than 0. This means you can draw a small bubble around x and still it is around or well inside your set. If we like to see a diagram describing this, if this is the set of A, so if you have an open ball around x, so the open ball all entirely with all of its points will be inside this set of A. And you will see it shortly in this diagram. Also, I made it for you. This is A, and that's the open ball of x, which is completely inside the set of A. Of course, internal of A, it's away from its corner or from its boundary. So internal of A, its x belongs to Rn, such that there exists r greater than 0, such that all the open points x and r are a subset of A. And exactly the same in our slides, but instead of dealing with r, we usually use epsilon. So let's see, is a subset of Rn, A is a subset of Rn. A is said to be interior to C, so we are talking about C is the bigger one, A is the smaller one. So the definition here is defined that this is C, the bigger set or the main set, and this is A, the element. We say that A is an interior of C if there is an open ball with r greater than 0. It's completely inside the interior of C, and we usually symbolize it by internal of C or N2C. As I told you, this is the definition of the interior. The exterior will be exactly the vice versa of this, or the converse of this. So let A is a subset of Rn, the exterior of A, denoted by XA, happens when you have your point or open ball completely outside the set of A or inside the A complementary. It can work both sides. So if this is C, this is gonna be A, and in this case, it's gonna be the external of C, which means that A already exists outside the frame of C and away from the boundaries of C. And it can be described as the following. Remark the two symbols, external of A, which means it's already exists outside of A, and also it's exactly equal to the interior of A complementary. A complementary, it means all the other elements outside A. This is A complementary. All the elements inside, outside A, this is what it's called A complementary. If we consider this is A with all the points inside it. So to have an exterior set, it should be an open ball outside A, which means it's an external of A or within the interior of A complementary. Of course, AC is the complement of A, interior of AC is the interior of the complement. I thought it is better to write the symbols and to explain them for you. Once more, here is A, that's an open ball inside, so this is the interior of A, that's the exterior of A, so XA, it means all the points that's located outside the set of A belongs to Rn, and they are already subset from A complementary, which represents all the space as you can see here. Same definition, exactly the same. C subset of Rn, A subset of Rn. The set of C complementary, it means all the other points that exist in Rn but not in C, of C. A is said to be exterior to C if there exists epsilon greater than 0, such that the open ball of A belongs to or subset from the C complementary, exactly the same. Remark also, this is exactly leads to, and vice versa, to, that's the open ball intersecting C is equal to phi. So that means the open ball of A, it's located completely outside of C. So the intersection will be phi, as you can see. And we usually symbolize it by external of C. Okay, what do we mean about the frontier or the boundary of a certain set? It means the elements on the edge or the trace around this area. So if we are once more back to our set, the boundary or the frontier, it is all the points as you can see on the boundary, just on the boundary of A, and it is equal to the intersection between the internal and the external of A. Usually we use, the internal and the external of A and the A complementary. So we usually, the frontier also called the boundary of the set of A denoted by partial A, and it is the set of points where every open ball around the point intersects both A and its complementary. So really, these points intersects this open balls between the A complementary and the A, or the A complementary and the A unit, or the set, as you can see. Okay, A dash is the closure of A, which stands for, as we will see in the coming slide, a closure, it means min. It means the internal points plus the boundary. And A, C dash is the closure of the complement of A. As I told you exactly, this is the border around our set, which is the intersection between the closure of A, which is inside and the boundary, and the closure of A complementary, also the points and the boundary of the external unit. Also, remark the definition, how it's written here. Let's see is a subset of Rn, and the A belongs to Rn. A is said to be border of C if for any epsilon greater than 0. Remark that the open ball in A intersection C doesn't equal to phi, simply because the borders are joined between both of them. Okay? Same way like for the other part here, which means the open ball at A, which intersects the C complementary, which also doesn't equal to phi, which means there is an intersection action. So it intersects points in front of C, is called the frontier of C and is represented by first C. Remark that the boundary of C equal the boundary of C complementary. So the boundary of any set, it's exactly the boundary is equal to the boundary of the set complementary, and these definitions and symbols are really very important. You have to understand them and you will feel them. So once more, that means any open ball around A intersection the C by itself, it's not gonna equal to 0. Why? Because they share the boundary. Same way like any open ball with respect to A intersection the C complementary also is not gonna equal to phi because they share the boundary as I told you. What we mean about a closure? The closure is the union between the interior point and the frontier or the boundary of a set. So simply we can define that A dash, which means A closure, and the set of A union its boundary. So it is the set and the boundary both together. This is what's called a closure of a set. So X belongs to N, and that's for every R greater than 0, B of X of R, intersection A doesn't equal to phi. Okay. Every point in the closure is either in the set or arbitrarily close to the set. Because if you have an open ball near the boundary, but sharing a point or some points with this boundary or with the set, so it's going to be involved in the closure of the set. The closure includes the boundary of the set, as I told you, and it is the smallest to close the set containing A. So if this is A, it is the smallest set that contains A. This diagram shows exactly what we are talking about. This is A and the boundary of it, and if there is a point that open balls that will share points with the boundary or A, this is going to be the closure of A. Exactly in a similar manner, C closure equal to the interior of C union its boundary, the frontier of C. And it's exactly the same. C union the frontier of C. So both of them work fine very well. Okay, what we mean about open and the closed sets? The open sets, by logic, it is the interior of a set without the boundary. But the closed ones, which contains the elements inside and there is a boundary around your set. So when there is a boundary, as I told you, C equal to its C closure. So once you have a set and it's equal to its closure, both of them equal to each other, identical, it means it is a closed set. But when you have a set and it's just defined on the interior sets without the boundary, it will be an open set. This slide will summarize all the information that we did go through. I thought to gather them all together in order to link the information and the diagrams all together and to be in front of your eyes all together working and as a comparison between all of them together. So once more, what we mean an open ball? An open ball, it means in 2 dimensions, it means that there is a circle and centered around the x node or the point, and here is R, which is greater than 0, but less than the distance connecting these 2 points, and there is no boundary, of course. It can be written like this. That's the symbol of an open ball. Also, I want to stress on that. I can also write it like this. B R of X node. Or if I'm using the epsilon notation, I can write it as B epsilon of X node. And that's the symbolization of an open ball. Okay, perfect. For the interior of a set, it is X belongs to Rn such that R is greater than 0, sorry, R greater than 0, such that the open ball is a subset of A, which means A is contained, or the open ball around X completely inside A, and that's the shape symbolizes what we mean about this. This is the set of A, and that's X node, which completely inside the set of A. On the other hand, for an exterior of a set, it means this X node and this open ball will belong to the other part, or the external of your set. So once more, this is A, this is the only points that lies in the interior of your set, and that's external of A, all the points outside your set. And of course, it's equal to an interior of and it's considered as interior of the A complementary, or all the elements of Rn except A. For the boundary, it means that for A closure, intersection A closure complementary, once you intersect these together, we are talking about the boundary or the frontier of a certain set. What we mean about a closure? The union of any A and its boundary. That's what we call about a frontier, as you can see. I believe this slide summarized the 5 definitions of open ball, interior, exterior sets, frontier, and closure, as you can see. Of course, C closure equal the interior union the frontier of your set, and it's also equal C union the frontier of C. So it's really very important, these definitions and these conditions. Some of the properties linked to these definitions, which are really very important, and I think I sent you the PDF for this part on your WhatsApp, so you will find them easily, inshallah. This theorem states that, let's see a subset of Rn, then the interior of C, remark, I want you to take care about this, or to think about this. The interior of any set, union its frontier, its boundary, union the external of a C, it will equal to Rn. This is exactly right, because what we wrote here is, if I have a C set, this is C set, so these are the interior of C, that's the frontier of C, and all of these points, that's the exterior of C. If you get the union of the interior and the frontier or the boundary and the external of C, you will get Rn, the whole space. And this definition is very, very nice. Also, for these notes, it's really very important. The interior of a C intersection the frontier is equal to 5, because there is no point joined between the frontier and the interior. And exactly the same, if you have the exterior and the frontier, their intersection also will be will equal to, this is what I'm talking about, their intersection equal to 5. And of course, there is no intersection between the interior of a C and an exterior of a C. النقط اللي واقعه جوه والنقط اللي واقعه بره ما فيش بينهم اي تقاطع يعني. طيب جميل حلو. Third, let's see be a subset of Rn. Then C is closed if and only if, and the C is open when. Okay, here's the definition: accumulated points and the isolated points and the derived points. It is open once you have a set. It's open once you have the interior of the set without the boundary. And it is closed once you have a solid boundary for this set. Okay, what we mean about accumulation points? Remark about the definition that I will tell you how to know it. A is said to be accumulation point of C if every open ball, so B of the open ball of A with radius epsilon, centered on A, contains at least one point of C. So for any points on the neighborhood, for any points on the neighborhood of C, where its open ball gather some points from C or its boundary, this is gonna called an accumulation of A. Think of it as a limit. If I took the limit of certain number or of certain mathematical expression, it will tend to a certain or a specific value. This is what we mean about accumulation point. Okay, what's the difference between an accumulation point and an isolated point? Isolated point, it is the points that are centered or are inside certain set by itself. And we will have an example shortly. What are the drive points, or it is the set of accumulation of points of C. This is what we call it the derivative of C, or the derived set of C. Here's once more definitions and more information, clarification about the accumulation points. Stated that any point x belongs to R is called an accumulation point of set A if every open ball around x contains at least one point as we defined it. X is an accumulation point of A. That means every point or the open ball except x by itself intersection A doesn't equal to 5. Once we say doesn't equal to 5, which means there is an intersection, so they are sharing points. Which means if there is in the neighborhood some points that once you take a limit, it will tend to be inside or on the border of this set, then this is going to be the accumulation point, or this is what's meant by accumulation point. Isolated points, it is the point, specific points by themselves. So if you have an open ball around this point, it will be completely inside your set. So a point x belongs to A is called an isolated point of A if there exists some open ball around x that contains no other points of A. So if you have this condition, you will have isolated points. So once more, x belongs to A is isolated. That's there, that there is, for every r greater than 0, there is an open ball intersection A, and the intersection is equal to this specific point. So we are talking about the elements or the points by itself, a point by a point. Okay, what are the derived set? It is the set of all accumulated points. We usually take the notation A dash for the accumulated points, or the derivative point for this example, or for this set. In order to show this on an example, this is really very important. See this finite set, which contains 1, 2, and 3. This is just only the set. Set A is the set of numbers which are 1, 2, and 3. So if you look to this set, which formed only from these two numbers, there is no open balls around this set which will share points with 1, 2, or 3, because the set contains just only 1, 2, 3. So there is no accumulation points, relative or limits that will tend to numbers containing 1, 2, 3. So there is no accumulation points here. Since there is no accumulation points, there will be no derived or derivative points related to this set. So what are the isolated points that exist in this set? They are 1, 2, and 3, because completely 1 is inside the set, and 2 and 3, they are inside the set. So once more, this is just a finite set of 3 isolated points on the number line. So there are none. Why? Because there are non-accumulative points. There is no matter how small an open ball or interval exists, it will never interfere with these values 1, 2, and 3. If you want more clarification, let me do this. This is the number line, and that's the x positive infinity and negative infinity. These are the numbers, just only 1, 2, and 3, and that's the set that we are talking about. So the set contains 1, 2, and 3. There is no number here with an open ball that will be shared with 1, or with 2, or with 3 in any location. So this is why there is no accumulation point, and this is what have been explained or what's explained in this short paragraph. Once more, these are the points. So the driven is equal to phi or equal to 0. There is no accumulation points. The isolated points are 1, 2, and 3, as you can see. So each one is isolated because there exists some small interval around each one of them, just only contains these points, which are 1, 2, and 3. On the other hand, if you look to this sequence, which states that I have 1 over n, and n belongs to a set of natural numbers, so I will have the set, which is infinite set 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, up to infinity. So if you look to the accumulated points, you will find these points. First of all, if we get back to the number line, this is the number line. Here we go. And that's the x-axis. Okay, here's 0, and here's number 1. This is 1 over 2. And this is 1 over 3. And that is 1 over 4. And that's going to be 1 over 5. As you can see, although 0 is not an element of the elements of this set, but it is a combination point. Because if you take n tends to infinity, you will have 1 over n, which is the generating term or the general term of this sequence, will end to be equal to 0. So if you take the limit of n tends to infinity for 1 over n, it's going to equal to 0. And to all the elements of this set belongs to the interval from 0 open up to 1. So the accumulation point, all of these will be accumulated, or 0 will be accumulated to this set. So this is exactly what we mean. This is a finite set, but all the points are spread out along the interval 0 and 1 of the real number. The accumulation point, the point 0 is not in the set. As I told you, 0 is not in the set. But the value of 1 of n get closer, this value will get closer to 0 as n tends to infinity, so 0 is considered an accumulation point. And the derived or the driven point, okay, this is the accumulation. Just a second. The derived set is going to be a dash equal to 0. This is the only accumulation point that exists here. So for the isolated points, all the fractions half by in specific 1/3, 1/4, it's called an isolated points. So A equal to A itself is a set of isolated points, as I told you. I hope this example shed the light exactly on the differences between the accumulation point, the isolated point, and the driven definition. Okay, this example also is really very important because it will also make things more clearer for you. So let's go through it step by step. Just in a second. Okay, here we go. Here it's given a definition. He wants you to indicate the interior, exterior, boundary, adherence, which means the closure, derivative, and the isolated points of the set, which consists of the set that we are dealing with, consists of xy, which are belongs to r squared, 1 minus x squared minus y squared greater than 0, and y minus x squared greater than 0, and union this sequence of this set. Let's first determine these ones. So I'm dealing with 1, I'm dealing with, let me start from here. I'm dealing with 1 minus x squared minus y squared greater than 0, which indicates that I have x squared plus y squared greater than 1. That means the interior of a unit circle, but without the boundaries. So if I want to do the x-axis and the y-axis, here we go, this is the x-axis, and that's the y-axis. For x squared, y squared equal to 1, this is going to be the circle that we are dealing with. But remark that this circle is open, as you can see, because we don't have the closure of this set. So this is mainly the first shape that's controlling the boundary or shaping the area that we are talking about. And y minus x squared equal greater than or equal to 0. Sorry, this is y minus x squared greater than or equal to 0, which means y greater than or equal to x squared, which represent a quadratic function, second degree parabola, starting from 0 and going up like this. So the area that we are talking about, or the region that we are talking about, it is this region. This is the region that we are interested in. This is actually x squared plus y squared less than 1, and that's y is greater than or equal to x squared curve. It's not just only this set. Remark the identification of the set. It has at these 2 points, here you have a boundary included in your set, but on the other half of this lamina or lens or whatever, there is no boundaries. It's an open part of your domain. Also, this is the union of 1 over n and 0, where n belongs to in capital, and as you can see, this is the shape that we are talking about. In order to determine the interior, so that's the interior of your region. Okay, so I will answer, is it open or not? Of course, it's not open and it's not closed. This is very, very obvious. It's not open because a part of your boundary is closed. And it's not closed because the other part of your boundary is an open boundary. So you are breaking from the two sides the idea. This is even away from even